In the field, Sherpa are like friends in the warehouse. So they do all the hard work and never get tired. So AMRs frequently operate in varied conditions, indoors and outdoors, with possible hazards or even uneven floors and debris, water, etc. So mechanical designs must be adaptable to different terrains and environments, which call for better drive systems, subsystems, and protective enclosures. I graduated as an industrial production engineer. So I started going into understanding of process development in my first job. Then there was a design interest for me. So that is when I shifted after 1 year of understanding all the processes and manufacturing process. I shifted to design, product design. So way back in 96 around. So it was like, I was interested in drawings basically. So I started with the drawing board. Most of the time 3D CAD was not there.
Yeah.
So almost my 4-5 years of experience was in drawing boards, where I used to do all 1:1, 1:1 scale, and I got the feel of what is what is centimeter, which nowadays we don't get in the computers, right? The generation. So that with that background, all my 3D designs were 2D. Basically, I had to do views and different views to make the product, right? So that's the way I grew up. And one more interesting thing is, it's when you want to do a perfect design, you have to go and understand what are the process steps. So every product that I designed in my career, so I went and I to see how the parts get made, and that understanding made me very strong mechanical engineer, and that continued for the years. So the initial foundation was very good. My career started in Pune. So, and it's like sort of ending in Pune again. Between that, I had many interesting experience across the globe. I worked in many industries. So the memorable experience, I would say, is the foundation that I got in the products that I made in my first 5-6 years of my career. So it was more like even they are running today. So they are in operation even today. They are making a lot of profits to the organization. And even if I go today to that company, I can see my products running, and even the tools and fixtures that I made. So all are operational. So that is the the quality or the reliability that I learned during my career. So that strong fundamentals has helped me, to take up more challenging roles. Yeah. So the initial experience that I got made me more and more interested. So as I went into industrial production, I learned the different casting process and all the manufacturing processes. And after that, I joined machine tools, where I learned the foundation of how things get made. And that interests me a lot, because I had a creativity within me. The creativity plus engineering combination, made valuable products. So that I could see physical things happen in front of me throughout my initial years. So every day I used to do some design, and the next day it will go for manufacturing, and within a week I'll see the products getting made. So that made me really the feel of whatever you have designed, and perfectly you get that made. So I was even mentored by a very senior person. So that learning, that I got, and the success in all my products that's happening. So that keep on building my interest. My career, like, it has been diverse throughout my throughout my career. Like I started with machine tools, then I joined a multinational company, a consulting company where I was deputed to USA. I worked on forklift designs in my initial career. Then I worked on various diverse products, machine tool SPM designs for another very leading bearing manufacturer. So I built the complete test lab for them. So this that's also very interesting. In US it happened. So after that, I came back to India. Then I started designing robots. So maybe around 8 years back, I did my first unit loader vehicle, and then I also built a pallet more. So grounds up, everything grounds up. So far, I was doing mostly static machines, industrial machines. So the new challenges came when you design mobile vehicles. So the strong fundamentals and the engineering approach. So that made me to successfully develop the first proto itself. It was almost close to production. Similarly, for the pallet more that I developed. So the very first product was very challenging, and it was somewhat the innovation came out like globally. It was one among the top few products in the world. So the innovative design principles and all. So that gave me a sense of very high happiness. I also did a lot of consulting for AGVs before even AMRs. So that all helped me, and you know, it so happened that you know I was I got just a call from would you be interested? So looking at my background, I also did a lot of patents. Around close to 130 patents has been filed, all in the area of robotics and automation. So this was kind of that's how I got a call from Saurabh, and it's just would you be interested? So that's how it happened. Yeah. Everyone in the engineering team understands that the new products that we have to deliver with quality and speed. So if we delay on this, we are no longer first to market. So we have to strategize our complete mechanical team design to focus on some of the products. I mean, focus on few products so that we deliver with speed. So rather than taking up many things and not getting all in time. So that is one thing. And learning from failures and maturing the product is no longer the right approach. Like it is fine initially, but now we cannot afford to do mistakes. So to reduce these iterations, firstly we have to take the approach of do it right first time. That's very important. In case we slip on very few unpredicted errors, for example, in the new product development cycle, we have to immediately fix and proceed. So to make a robust new product, not only we should show the design perfection, we have to imagine also how the products are getting made, and in manufacturing, and how things can go wrong in manufacturing. So once you take care of all this, we are close to production ready. So the last thing we want to see is any design leading to field failures. Say for example, we have two design approaches for a particular design. So two options basically. One option, we have a linear bearing design, which is a ball bearing design for a suspension mechanism. Another option could be a polymer bearing design. So now when it comes to, you have to choose between one is costly, one is cheap. So what happens is, like, you have to do early stage testing. So you have to do the life testing, accelerated life. You have to quickly build a test setup. So this test plan goes hand in hand with the design process. So these are some of the key things. And so having done all this, now comes the reliability. To make a reliable and robust product, first expertise in the team, that is very important, and the maturity of the team. Our engineers are churned with various experiences, and they will learn over the years. So every engineer understands, like going from design, the mistakes, if it happens, the cost of quality basically, if it happens from design to proto to pilot to production or to field implementation, it skyrockets. So it's very costly to fix anything in the field. So all this understanding help us with the best practices, developing the best practices to make world class products. The key aspect is we have to spend more time in planning phase, which is pre-engineering phase, and we do a thorough market study, customer benchmarking, and we have to see identify the top risks in the engineering phase. We have to and the top risks and the long lead design cycle items. So we need to address that so that we are fast to production readiness. To make the product versatile or modular in most number of applications, a thorough customer requirement and environment understanding, and customer benchmarking, robot study, and to identify how different and innovative we can make our products so that it earns more revenue to the company. So this is the right approach we follow. And for the reliable products is a byproduct of a few things: the right processes that we follow, the expert engineers who have been churned through the various learnings, and also the support that we get from industry and academia who support our mechanical engineering team. So we also focus on continuous improvements for during the process of development, and also any post-mortem learning events. So in recent years, many new ideas have helped our mobile robots, Sherpa robots, to work better and smarter. I'd like to quote a few examples. Robots now have mechanical redundancy for safety. It's another part that can still keep things safe. For example, Sherpa robots have a fail-safe brake. That is, if the power is lost, uh, robots never moves in this condition. So this helps avoid accidents and keeps the surroundings safe. So another important item in a mobile robot is the transmission. So they are made more efficient so that they waste less energy from heat and friction. So that the robot can work longer between two battery charging. So, to increase the efficiency is not just choosing the right gearbox of the right quality, the backlash, low backlash, etc. It's about the all the parts that go into connecting between the motor, gearbox till the wheel. So, have we used the right grades of steel or aluminum materials, and the right process of manufacture for every part that go into this tolerance stack. Uh, for example, the load carrying members are made heat treated for strength, and the part accuracies are maintained for all the critical to quality parameters. Uh, yeah, another trend is the usage of light but strong materials. We need to deliberate where we have to use light materials and where we have to use strong materials. Uh, Robot makers have used a special fiber like glass fiber or carbon fiber materials. They give strong structure without being heavy, so that the robot uses less power. So they also do not rust, and also vibration reduce the vibrations, and they are also transparent to Wi-Fi signals, and which are getting blocked by metal. So these advancements, some more examples to quote, like 3D printing has been in the industry for many years, but the difference is it is accessible to every engineer now, unlike because of its low cost and the high technological advancements that it offers now as compared to earlier years. So every engineer quickly makes the robot products, mechanisms. They test the mechanisms very quickly and mature the design. So another one to talk about is what was very privileged with few engineers earlier days, like FEA was very niche skill for FEA engineer. Now in our team in Ati Motors, we have every engineer working and doing his own simulations because the software also has become very user friendly, and it's not only we stop at simulations, we go back and test it in real using probably strain gauges, and we fine tune our model to fix and optimize the results. So that's one thing. And another thing is when it comes to mobile vehicles, unlike static structures, we also have to do multi-body dynamics in simulations in some cases where we need study the trolleys, stability, etc. Yeah. Another one aspect of advancement is the battery swapping. So, based on the customer requirements, we can do automated battery swapping or manual battery swapping based on the time available, maybe in seconds or minutes. And yet another way of addressing is opportunistic charging, like when the vehicle has to take a break, like during lunch breaks, or when the operators take a break, or the shift change happens, the vehicle can go and get itself charged automatically. So these all sophisticated mechanisms are built in the mechanical design. Ati Sherpa robots are just not wheeled robots. They are packed with unique features. To develop innovative features, we ask the following like questions. We ask few questions: is a new product going to earn more profits with less cost? Can we deliver a product that can do more with less? How can I make it unique and a market differentiator? Is the product scalable? Is the product adaptable? Etc. We keep brainstorming and come up with our own unique solutions. A scaled up version, for example, we have our highly matured low payload product, which is Sherpa Lite. So we have developed another variant of it, which is the 10,000 Sherpa 10K, which can pull up to 10,000 pounds. It's equivalent to pulling 3 to 4 cars, and still in the smallest form factor to maneuver in tight spaces than others. You know, all Sherpa triggers, including this, also can do indoor and outdoor terrain, from smooth floors to concrete to tar and etc. So while majority of AMRs are addressing only indoor. So we have another product, Sherpa 500, which is also modular based platform that moves. On top of it, we have developed payload lift option, turntable option, roller option, etc. The same modular platform transforms itself into a humanoid, like a Sherpa Mecha. This itself is a new platform. And with various innumerable number of gripper options, the humanoid can do different tasks. It can come up with, it also has a quick change tool option. So the tool also is automatically getting changed. Making a bot with a single application is very easy, but the challenge comes when you have to combine different applications where there is hardware software challenges, and you have to address this. So we have overcome this successfully and made our vehicles as far as possible modular and innovative. Yeah, robustness and reliability are very essential, but because our vehicles are subjected to unpredictable loads, and innovation in structure and sensing and controls are needed to meet unique requirements. These are the demands of the autonomous systems. So, selecting durable materials and ensuring environmental protections through appropriate coatings is crucial for long-term reliability, especially when the robots are deployed in harsh and corrosive conditions. Secondly, the powertrain must be optimized. And to list a few design best practices, especially for mobile robots, lowering the center of gravity, optimally placing the parts within the AMR, widening the wheels for better stability, reinforcing the chassis structure, improving suspension and dampening, and applying bolt talks. So you have made a fantastic vehicle, but if you don't tighten the bolts, that's a very failure point. So and load cells to measure payloads, etc. So not only this, we also do statics and dynamic analysis, like toppling studies are very essential. Analyzing all the possible load cases, braking loads, operating loads, impact loads, then centrifugal forces during turning, step climbing, ramps, ditches, bumps, and then fatigue loads is one more aspect to where the fork picks and drops continuously every cycle. So all these are analyzed. That's the way Ati robots are very strong and robust for to work in warehouse. The outer chassis itself, it blocks the dust and impacts and water splashes. The robot is built with good metal and right coatings so that it does not rust and wear. All the robots are made functional performance and ensuring the durability and stability without compromising on aesthetics. So all the Sherpa designs have safe design. All moving parts are covered with bumpers and smart sensors to stop accidents and protect the people. So these choices are making Sherpa robots, keeping them working for a long time without much trouble. So pallet movers, for example, they are deployed for higher payloads and but hit their limits when it comes to extremely tight spaces. So when we study customers in India in most of the production and factory scenarios for raw material, work in progress, and finished product handling to and fro in the production lines, we notice that there are extremely narrow aisles and pallet mover doesn't work in such. They are handled by HOPTs and VOPTs, and it's mostly in some cases it's transferred by bins or pallets or small pallets or containers or trolleys. So in these cases we had an existing product which is called a Sherpa pivot, which was used for assembly line movement predominantly for that. So what we did was we took the chassis part alone and we added forks to it at the end, and we converted that into a like a mini pallet mower, which can carry the items by itself and move it in the tight spaces. It became a very miniature vehicle. So this was brought because of the small change that we did to existing vehicle, and it went into production live very fast. So this is a kind of reusability in the design. Existing design was reused to create a new product and bring it to life in an extremely low development time. Ati's full stack way of building robots means mechanical, electrical, and software teams all work together from the very start. For example, if the control team needs the robot to be extra accurate, the mechanical team optimizes the things, which include the steering, gearbox, wheels, suspension, etc. so that the mechanical team gives the best product, best outcome comes, so that the software team or the controls team don't have to work upon the inaccuracies, but they just have to focus on their part. So it's like everyone playing a music band, and they fine tune the instruments together to make a right music. So also the robot moves well and works as planned in the real life. By having the teams design together, the Sherpa robots are finished faster and ready to customer needs, because all the problems are solved in the beginning itself, and every robot is built to the best capability. The teamwork helps make sure robots can do tough jobs. At Ati, we follow also concurrent engineering approach to reduce the development time and maturing the overall development from proto to production readiness to meet future customer demands. Because we often get orders, and we have a deadline to work. So all system engineers in Ati have understanding of what customer design defines as value to deliver a product that meets customer needs and has a capability to be manufactured. In the field, Sherpa are like friends in the warehouse. So they do all the hard work and never get tired. So AMRs frequently operate in varied conditions, indoors and outdoors, with possible hazards or even uneven floors and debris, water, etc. So mechanical designs must be adaptable to different terrains and environments, which call for better drive systems, subsystems, and protective enclosures. Modular and scalable designs help reduce cost and facilitate easier upgrades, but creating such designs that are also robust and efficient is a challenge that we have to overcome this. One example is adaptability to change job. So Sherpa lifter can change its top part. It can lift things. It can do tunneling applications. It can move stuff on conveyor. So similarly, the product Sherpa Flex has the same body for all, but the fork part can change. It can have one fork, it can have two forks, or it can become a pivot. So for moving things like an assembly line. So high payload capacity in small space is what we have developed with Sherpa 10K that can pull up to 5 tons. So even in tight spaces, it moves easily. So similarly, our Sherpa pallet movers, the chassis are sleek and able to lift heavy payloads. So the maneuvering is one more aspect which is very important. So, and we have addressed this in our robots. So we have robots that can do in place turning, and also the robots that can do with a minimal turning radius. So not only on the products, we also developed accessories like a trolley with 4 wheels that can turn using special steering mechanisms. So these help Sherpas turn in small spaces as well. So Sherpas robots are smart, strong, and can do many jobs in big or small spaces without problem. So the mechanical frontiers of AMR like Sherpa is broad and thereby very exciting and challenging. An example of do more with less is smart modularity. How can we develop a pallet mover type mobile robot that can do multitasking? Can we lift all the pallets in the world? Can we, for example, pallet sizes may vary in width and length. It can be a closed type pallet, closed stringer type, or a open stringer type, open type pallets. The pallets may vary in material, for a wood or steel or metal. It can be standard pallets, it can be custom pallets, and there are many trolley applications also which need to be. So what if we can provision adjustment for fork to fork distances, so that for wide pallets we can make it more stable. Similarly, we can snap on forks closer for addressing small trolleys. We can add a tilt angle so that when we have to move fast, we'll tilt the load and make it to backrest on the chassis so that it's more stable for high speeds, like that. So a few customers only want ground level transport, whereas some want to stack one top of the other, and some want to stack on a rack, or sometimes it can be going inside the truck and unloading the pallets. So these are the various needs of the customer. The challenge is what we think is how to address all this and make one product that will work for all this. So these are the future directions we are thinking on development of products. See, to derive one solution for all these needs, make it very challenging and interesting. These are the futuristic kind of directions we take. Also, there's one more aspect: bio-inspired designs. So we are seeing robots that are moving like animals or humans for greater agility, and this is become a dream come reality for Ati. We have the Sherpa mecha at Ati. So our humanoid with the strength of AI and unique mechanical design has a countless number of applications based on the customer specific tasks. We can change the grippers accordingly to perform the pick and place or the assembly or the testing operations, as the case may be. Mechanical engineers will keep driving the AMR revolution. When we expect the robots will become stronger with lighter materials. So robots will carry more with less and become more energy efficient. They will last longer with greater reliability. So if you are, they will also be able to easily to fix and serviceable. So AMRs have integrated sensors everywhere. So it is like a mechanic. The robots will have a mechanic grip with a bat's sense of sensing. So that's the futuristic way we are thinking. And mechanical engineers will collaborate to the core with all the teams and build the best robot to push the boundaries of what robots can do.